Good afternoon all. Last day we have finished with the problem. The problem is show that the matrices M1 1 0 0 0, M2 0 1 0 0, M3 0 0 1 0 and M4 0 0 0 1 form a basis for the vector space M22 of 2 by 2 matrices. To show that a set of vectors S is a basis, we have to show that it is linear. The vectors in S are linearly independent and it spans the whole set. So we have to show that M1, M2, M3, M4 form a basis. We have to show that M1, M2, M3 and M4 are linearly independent and M1, M2, M3 spans and M4 spans M22, the 2 by 2 square matrices. So first we have to show that it is linearly independent. For that, consider C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 equal to 0. That is C1 into 1 0 0 0 plus C2 into 0 1 0 0 plus C3 into 0 1 0 0 plus C4 into 0 0 0 1 equal to 0. That is C1, C2, C3, C4 equal to 0 0 0 0 implies C1 equal to C2 equal to C3 equal to C4 equal to 0 implies M1, M2, M3 and M4 are linearly independent. Now consider we have to show that this spans M22. For that, consider some 2 by 2 general 2 by 2 matrix. Some B is equal to A, B, C, D and can be written as C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 equal to B. That is C1 into 1 0 0 0 plus C2 into 0 1 0 0 plus C3 into 0 0 1 0 plus C4 into 0 0 0 1 equal to A, B, C, D. that is C1 plus that is matrix C1, C2, C3, C4 is equal to A, B, C, D, which implies C1 equal to A, C2 equal to B, C3 equal to C, and C4 equal to D. Implies this M1, M2, M3, M1, M2, M3 and M4 spans M22. That is M1, M2, M3, M4. We already shown that it is linearly independent, so it's also spans M22. So M1, M2, M3, M4 form a basis for M22. Now next problem is show that the vector space Pn of all polynomials with real coefficients is infinite dimensional by showing that it has no finite spanning set. So we have already shown that the finite polynomials is a vector space, and we also show that the infinite number of polynomials is also a vector space, but we have to show that for an infinite dimensional polynomial vector space, it does not have no finite spanning set. For that we are using the contradiction method. We are assuming that there exists a finite spanning set for Pn. So we have to take say P1, P2, etc. Pr. Then the degrees of the polynomial would have a maximum value n. And this in turn would imply that any linear combination of polynomials in S would have degree at most n. നമ്മൾ പോളിനോമിയൽ അതുവരെയുള്ളത് എടുത്തു, P0, P1, etc. PR. ഇനി അതിലും കൂടുതലുണ്ടെങ്കിൽ ഒരു n+1 ഉണ്ടെങ്കിൽ n വരെ ഉണ്ട് മാക്സിമം എന്ന് അസ്യൂം ചെയ്തു. Then there would be no way to express the polynomial x raised to n+1 as a linear combination of the polynomials in S. നമ്മൾ പിന്നെ അതിൽ നിന്ന് അല്ലാത്ത ഓർമ്മ എടുത്തു, എക്സ് റേസ് ടു എന്നിലും കൂടുതലുള്ള എക്സ് റേസ് ടു n+1 എടുത്തു കഴിയുമ്പോൾ നമ്മൾ എക്സ് റേസ് ടു n വരെ ഉള്ളൂ എങ്കിൽ വി കാൺ റൈറ്റ് ദ ആസ് എ ലീനിയർ കോമ്പിനേഷൻ ഓഫ് ദാറ്റ് പോളിനോമിയൽസ്. അപ്പോൾ നമ്മൾ സ്പാൻ ചെയ്യണമെന്ന് പറഞ്ഞതിന് കോൺട്രഡിക്ഷൻ ആവും, കോൺട്രഡിക്റ്റിംഗ് ദ ഫാക്ട് ദാറ്റ് ദ വെക്ടേഴ്സ് ഇൻ എസ് സ്പാൻസ് വി. So it means it does not have a finite spanning set. The spanning set will be also infinite. Now next we have a definition for coordinates. If S equal to v1, v2, v3, etc. vn is a basis for a vector space V, and if v equal to c1, v1 plus c2, v2, etc. cn, vn is the expression of a vector v in terms of the basis S. Then the scalars c1, c2, etc. cn are called the coordinates of v relative to the basis S. The vector c1, c2, etc. cn in r raised to n constructed from these coordinates is called the coordinate vector of v relative to S, and is denoted by v suffixes, and it's an order c1, c2, etc. cn. So നമ്മളിപ്പോൾ ബേസിസ് കണ്ടുപിടിക്കുമ്പോൾ ബേസിസ് സ്പാൻസ് ദ സെറ്റ്. അപ്പോൾ നമ്മളൊരു ആർബിട്രറി വെക്ടർ എടുക്കുകയാണെങ്കിൽ ഇറ്റ്സ് വി, അതിന് നമുക്ക് c1, v1 പ്ലസ് c2, v2 പ്ലസ് എക്സെട്ര cn, vn എഴുതാം. അതിൻ്റെ കോഎഫിഷ്യൻ്റ് ആയിട്ട് വരുന്നത് അതാണ് കോർഡിനേറ്റ്സ്. വി ഹാവ് ആൻ എക്സാമ്പിൾ. In the special case, let v equal to r raised to n, and S is the standard basis. The coordinate vector v of S and the vector v are the same, that is v equal to vs. For example, in R cube, the representation of a vector v equal to a, b, c as a linear combination of the vector in the standard basis I, j, k is v equal to ai plus bj plus ck. So the coordinate vector relative to the basis is v suffix s equal to abc, which is at the same as the vector v. നമ്മളിപ്പോൾ ആർ ക്യൂബിലാണ് ഇപ്പോൾ എടുത്തേക്കുന്നത്. എബിലും ഏത് അതിൻ്റെ കോർഡിനേറ്റ് വെക്ടർ എന്ന് പറഞ്ഞാൽ എ ബി സി ആയിരിക്കും. കാരണം നമ്മൾ സ്റ്റാൻഡേർഡ് വെക്ടർ വെച്ച് എഴുതുമ്പോൾ എ ഐ പ്ലസ് ബി ജെ പ്ലസ് സി കെ എന്നാണ് ഇത് വെക്ടറിന് എഴുതുക. അപ്പോൾ അതിൻ്റെ ഐ ജെ കെയുടെ കോഎഫിഷ്യൻ്റ് ആയിട്ട് വരുന്നത് എ ബി സി, അതായിരിക്കും കോർഡിനേറ്റ് വെക്ടർ. Now we have a theorem for uniqueness of basis representation. If S equal to v1, v2, etc. vn is a basis for a vector space V, then every vector v in V can be expressed in the form v equal to c1 v1 plus c2 v2 plus etc. cn vn in exactly one way. This is the uniqueness of basis representation. We have a basis, then we can represent every vector in a unique way. Now for the proof, since S spans V, it is a basis, so it is linearly independent and it spans V. So it's S spans V. It follows from the definition of a spanning set that every vector V is expressible as a linear combination of the vector in S. So there exists a linear combination expression. So we have to now show that it is unique. For that, we are taking one more combination to see that there is only one way to express the vector as a linear combination of the vectors in S. We are suppose that some vector V can be represented as v equal to c1 v1 plus c2 v2 plus etc. cn vn, and also as v equal to k1 v1 plus k2 v2 plus etc. kn vn. Subtracting the second equation from first one, we get c1 minus k1 v1, 0 is equal to 0 c1 minus k1 into v1 plus c2 minus k2 into v2 plus etc. cn minus kn into vn. So the right side of the equation is a linear combination of the vector in S. The linear independence of S implies that since it is a basis, it is linearly independent also. So it means c1 minus k1, each coefficient of the vectors v1, v2, etc. vn is 0. So c1 minus k1 equal to 0, c2 minus k2 equal to 0, etc. cn minus kn equal to 0. That is c1 equal to k1, c2 equal to k2, etc. cn equal to kn. That's the expression for v are the same. So we have given that it is spans. So we use the both things. So first we assume that it is a linear, it can be represented as a linear combination. Now next we assume that to prove the uniqueness, we assume that one more way to express, and we subtract the one equation from the other, then we got an equation, a new equation with a and its left side is 0, and we equate the each coefficient of vectors. So it means that c1 minus k1 equal to 0, c2 minus k2 equal to 0 implies cn equal to kn. That means this is if there exists an expression, it is in the unique way. Now we are moving to one problem. Find the coordinate vector for the polynomial p of x equal to c0 plus c1x plus c2x square plus etc. cn x raised to n relative to the standard basis for the vector space Pn. So, and the next problem is, so we can do that problem first. So first we are assuming, first we given that this is the p of x is the given polynomial, and the standard basis for the vector space Pn is 1x x square plus etc. not plus 1x x square etc. x raised to n. So given p of x is equal to c0 plus c1x plus c2x square plus etc. plus cn x raised to n given, and standard basis for p is 1 x x square etc. x raised to n. Thus the coordinate vector is coefficient of this one c0, c1, c2, etc. cn, coefficient of the standard basis in the given expression. Next problem is find the coordinate vector of b equal to abcd relative to the standard basis for M22. Today we have already shown that the M22, the basis for M22 is we have already shown it is 1 0 0 0 0 1 0 0. This is M1, this is M2, and M3 is equal to 0 0 1 0. This is 1. And M4 is equal to 0 0 0 1. B can be written as A into 1 0 0 0 plus B into 0 1 0 0 plus C into 0 0 1 0 plus D into 0 0 0 1 is equal to A, B, C, D. Therefore, coordinate vector for M2, coordinate vector for M22 with respect to standard, with respect to M1, M2, M3, M4 are A, B, C, D. Next problem is the vectors V1 equal to 1 2 1, V2 equal to 2 9 0, V3 equal to 3 3 4 form a basis for R cube that we have already shown earlier. Find the coordinate vector of V which is equal to 5 minus 1 9 relative to the basis S equal to V1, V2, V3. So we have to solve. Consider C1 V1 plus C2 V2 plus C3 V3 equal to V, where C1 into V1 is equal to 1 2 1, V2 equal to 2 9 0. 1 2 1 plus C2 2 9 0 plus C3 3 3 4 and V equal to 5 minus 1 9. 3 3 4 is equal to 5 minus 1 9. So we can write equating the coordinates. So C1 plus 2 C2 plus 3 C3 equal to 5. 2 C1 plus 9 C2 plus 3 C3 equal to minus 1. And C1 plus 4 C3 is equal to 9. Or we can write in matrix form as 1 2 3 2 9 3 1 0 4 we can write in augmented matrix AB is equal to 5 minus 1 9 to solve this matrix. So see, R2 changes to R2 minus 2 R1 and R3 changes to R3 minus R1. So this becomes 1 2 3 5 0 9 minus 2 into 2 4. 9 minus 4 is equal to 5. 3 minus 2 into 3 3 minus 6 equal to minus 3. Minus 1 minus 2 into 5 minus 1 minus 10 minus 11. This is 0. 0 minus 2 is minus 2. 4 minus 3 is 1. 9 minus 5 is 4. Now we have to change the second row by 1. So R2 changes to R2 by 5. So this is equal to 1 0 0 1 2 3 minus 5 minus 3 by 5 minus 11 by 5 minus 2 1 4. Now R1 changes to R1 minus 2 R2 and R3 changes to R3 plus 2 R2. Equal to, this is 1 0 0 and this will be 0 1 0 and this will be 3 minus 2 into minus 3 by 5. So 3 plus 6 by 5 which is equal to 21 by 5. This is minus 3 by 5 minus 11 by 5. This is minus 5 minus 2 into 11 by 5. So minus 5 plus 22 by 5. So this is 47 by 5. Now this is R3 plus 2 R2. 1 plus 2 into minus 3 by 5. So this is equal to minus 1 by 5. 4 plus 2 into minus 11 by 5. 4 minus 22 by 5 is minus 2 by 5. Now we have to change to R3 into minus 5 R3. So this is becomes R1 or R2 not change. So this is 1 0 0 0 1 0 21 by 5 minus 3 by 5 47 by 5 minus 11 by 5 minus, when we multiply with minus 5 this becomes 1 and this becomes 2. Now R1 changes to R1 minus 21 by 5 R3 and R2 changes to R2 plus 3 by 5 R3. So this becomes 1 0 0 0 1 0 1 0 0 and this will be 2 and minus 11 by 5 47 by 5 minus 21 by 5 into 2. So minus 42 by 5. 47 by 5 minus 45 5 by 5 and that value is 1 and minus 11 by 5 R2 plus 3 by 5 R3 minus 11 by 5 plus 6 by 5. So this is minus 5 by 5. So this value is minus 1. So therefore this means C1 equal to 1, C2 equal to minus 1 and C3 is equal to 2. Therefore coordinate vector VS is equal to 1 minus 1 2. Now the next problem is find the vector V in R cube whose coordinate vector relative to S is Vs equal to minus 1, 3, 2. So we have to find the vector. Here we have to, in the first problem we have to find the coordinate vector. For that we have to find the coefficient C1, C2, C3. For that C1, V1 plus C2, V2 plus C3, V3 equal to V. Now we know that the value of C1, C2, C3. Now we have to find the V corresponding to minus 1. Here C1 is equal to minus 1, C2 is equal to 3, C3 equal to 2 in the second problem. So we have to find V. So here in the second problem we have to find V such that C1 V1 plus C2 V2 plus C3 V3, and C1 is given as minus 1, V1 C2 is V1 is equal to C1 is equal to minus 1, C2 is equal to 3, 2, C2 is equal to 3 and C3 is equal to 2, V1 is equal to 1, 2, 1, V2 is equal to 290 and V3 is equal to 10, V3 is equal to 334. So V is equal to minus 1 into 121 plus 3 into 290 plus 2 into 334, which is equal to minus 1 minus 2 minus 1 plus 6270 plus 668, which is equal to minus 1 plus 6 plus 6, minus 1 plus 6, 5 plus 6 is 11, minus 2 plus 27 is 25, 25 plus 6 is 31, minus 1 plus, this is 0, minus 1 plus 0 is 0, 0 plus minus 1 plus 0 is minus 1, minus 1 plus 8 is 7. So this is the answer. 11, 31, 7 is the answer.